Alright, so if the sine of x to the power of 10 plus the cosine of x to the power of 10 is equal to 11 over 36, what is the sine of x to the power of 12 plus the cosine of x to the power of 12? Well, first of all, we're going to start off immediately with the substitution. So let's let y be equal to the sine squared of x. So this then turns into y to the power of 5 plus 1 minus y to the power of 5, since the cosine squared of x is equal to 1 minus the sine squared of x. And so this is equal to 11 over 36. So we have y to the 5 plus 1 minus 5y plus 10y squared minus 10y cubed plus 5y to the power of 4 minus y to the power of 5. So cancelling out these two terms gives us 5y to the power of 4 minus 10y to the power of 3 plus 10y to the power of 2 minus 5y plus 1 is equal to 11 over 36. So now subtracting 1 on both sides gives us 5y to the 4 minus 10y to the 3 plus 10y to the 2 minus 5y is equal to negative 25 over 36. So now dividing both sides by 5 gives us y to the 4 minus 2y to the 3 plus 2y squared minus y is equal to negative 5 over 36. So now factoring out a y gives us y times y to the 3 minus 2y squared plus 2y minus 1 is equal to negative 5 over 36. And it's about at this point that I kind of want to stop. While I can try to use remainder factor theorem to continue factoring this, I kind of don't want to, because even if I do manage to factor this entire polynomial, it won't really matter because there's still a negative 5 over 36 on the side, so I won't even be able to solve for y. And if I move the 5 over 36 to this side, then it'll become pretty cumbersome to solve this problem, because I'll have to multiply everything by 36, and I kind of just don't want to do that. So it's around this point that I wonder, can I make another substitution? And the answer is yes. Let's make the substitution z is equal to 1 over 2 minus y. We choose 1 over 2 minus y because it will balance out these two terms. So now substituting z in, we get 1 over 2 plus y to the power of 5 plus 1 over 2 minus y to the power of 5 is equal to 11 over 36. And now expanding both of these using the binomial theorem and then combining like terms, which I will not do on board because I don't feel like it, we eventually get 1 over 16 times 80 z4 plus 40 z squared plus 1, which is equal to 11 over 36. So now multiplying both sides by 16 will give us 44 over 9 on the side. So we get 80 z to the 4 plus 40 z squared plus 1 will be equal to 44 over 9. And now moving the 44 over 9 to the side will then give us 80 z to the 4 plus 40 z squared minus 35 over 9 is equal to 0. Multiplying both sides by 9 and then dividing by 5 will then give us 144 z to the 4 plus 72 z squared minus 7 is equal to 0. And then again, to save us a lot of time, I'm just going to tell you that the z is equal to the square root of 1 over 12, which is also equal to 1 over 2 root 3. Also, I just realized that I wrote y here instead of z, so 1 over 2 plus z and 1 over 2 minus z. So sorry I made that mistake, but I only noticed it because it is also true that 1 over 2 plus z to the power of 6 plus 1 over 2 minus z to the power of 6 is then equal to the sine of x to the power of 12 plus the cosine of x to the power of 12, which is what we are looking for. And so now you can either apply SR cubes or the binomial theorem, it doesn't really matter. Eventually, in the end, you will get 13 over 54. And so 13 over 54 is our answer, and we are done. Now, this is an AIME problem, so the actual problem did ask for 13 plus 54, so we get 13 plus 54 is equal to 67, and we are also done. So yeah, I did leave out a lot of calculations in this problem, but really, they're right, so just trust me. So yeah, thanks for watching, hopefully you enjoyed, and hopefully I'll see you next time.